In today's presentation, we will be discussing a non-Euclidean geometry called Taxicab geometry. So to begin, we will do a brief introduction. Suppose you live in the city below. You live at the intersection of B Street and 5th Avenue. Look for the star. That is your house. Your favorite restaurant, labeled by the heart, is at the intersection of 2nd Avenue and E Street. You want to go eat at your favorite restaurant because you are starving. How do you get there? If you could fly, you would follow the direct route shown below. So that would be following the diagonal route. You cannot fly, though. Your home does not have a helipad or a runway. You do not have wings, so you have to walk or drive, and we cannot walk or drive through buildings. What route would you take? How many blocks would that be? So one example is that you could go east 3 blocks and south 3 blocks for a total of 6 blocks. Could you take a different route? How many blocks would that be? So another route is that you could go south first and then go east, and it's still a total of 6 blocks. How about a more complicated route? How many blocks would that be? So you could go south, east, south, east, south, east, and it's still 6 blocks. So far, all our routes have been 6 blocks. Is there a shorter route? A longer route? So looking at a longer one, we could go west, south, east, north, east, south, and walk or drive a total of 14 blocks. But I don't think anyone would want to do that when you could have went 6. All of these examples, except the one where we flew to dinner, were examples of taxicab geometry. So think of a taxicab driving through a city. The flying example is an example of Euclidean geometry. This is what we normally teach in geometry classes in high school. So here is a visual of Euclidean versus taxicab. The red, the blue, and the yellow are all taxicab examples, and the green is a Euclidean example where we would typically use the Pythagorean theorem. So are all 4 routes the same length? So the red has a total of 12 blocks, as does the blue and as the yellow. But if we use Pythagorean theorem, the green has about 8.5 blocks. So the green is a shorter distance, but we can't always fly to our destinations or walk through buildings. So we usually have to take a more directional approach when driving or walking. So next you will be watching a series of videos which discusses Euclidean circle versus the taxicab circle. Enjoy.
In Euclidean geometry, you can see a circle easily by labeling the center and choosing a radius. In this case, let's choose a radius of 1. So 1 from the center, 1 from the center, 1 from the center, 1 from the center. And that gives us the circular shape that we are used to seeing in Euclidean geometry. Kind of rough sketch. Now in this case, with Euclidean geometry, the radius is 1 everywhere, even in the diagonal direction. You can see that these radii in the north, south, east, and west are easiest to see, but all of these radii still exist, diagonal from the center to the edge of the circle. In taxicab geometry, if we want to draw a circle, we can still recognize the center and go 1 unit for the radius to the north, to the south, to the east, and to the west. But in this case, you won't have any diagonal radii because we only measure distance in the x and y directions. So our circle under taxicab will actually resemble a square that we're used to seeing in Euclidean geometry.
Now that you have learned how to envision a Euclidean circle versus a taxicab circle, let's discuss these types of circles a bit further. Circles in taxicab geometry with center C and radius R is the set of all points R units from C. If we were to draw a circle in Euclidean geometry with a radius of 5, we would have a round shape demonstrated in the first figure here. In this figure, we note that there are exactly 12 lattice points that are exactly 5 units from point A. We can use Pythagorean triplet 3, 4, 5 to determine the distance between the 2 points. The lattice points for this circle are shown here. Using GeoGebra, we can create the circle using center 0, 0 and radius 5. As in Euclidean geometry, a circle is defined as the locus of all the points that are the same distance from a given point. In Euclidean geometry, the shortest distance between 2 points is a straight line like a flying bird. In taxicab geometry, however, circles are no longer round but take on a shape that is very unlike the circles to which we are accustomed. In our example, that distance is 5, and we can demonstrate this with a taxicab circle in the second figure. If we were to mark all lattice points that are exactly 5 units from point B, our resulting taxicab circle consists of 20 points, a neat way to square a circle. In taxicab geometry, the distance is measured as a taxicab would drive, and the lattice points are shown here in this second figure.
Here you see two drawings. The one on the left is a Euclidean circle with center C. The one on the right is a taxicab circle with center F. Both of these circles have a radius of 3. If you look here, 1, 2, 3, and if you look here, 1, 2, 3. Additionally, other points in this taxicab circle have a radius of 3. If I put a point here, point G is 3 units from F by counting 1, 2 in the x direction and 3 in the y direction. So the distance between F and G in taxicab geometry is also 3 units. How we would count the circumference on a taxicab circle would be to count each side. 1, 2, 3, 4, 5, 6. Each one of these sides is 6 units. 1, 2, 3, 4, 5, 6. So our circumference here is 24.
In the previous video, we saw a Euclidean circle with a radius of 3, or a diameter of 6, and a taxicab circle with a radius of 3, or a diameter of 6. So we've already discussed the circumference of the taxicab circle to be 24. To extend, we know from Euclidean methods, circumference is equal to pi, which is a constant, times the diameter. The question is pi the same constant in both Euclidean and taxicab circles? In a Euclidean circle, pi is the circumference divided by the diameter, which implies the distance around the circle is separated into diameter parts, and that will equal a constant pi.
So I have a circle here. This is the same circle as we saw in GeoGebra. It has a diameter of 6 or a radius of 3. And this is my diameter of 6. So I'm going to separate the outside distance of my circle into diameter parts. So there is one diameter. And we have 2 diameters. Here we have 3 diameters. And then we have a bit of space here. And we all know that that space comes out to be about 0.14159 ... So we can make 3 full diameters and a little bit of another diameter. So in a circle, our constant pi is about 3.14. So my question is pi the exact same constant value in a taxicab circle? So I have my diameter. I can make 1, 2, 3, and 4 diameters. So, pi in a taxicab circle is 4. So just as we see in taxicab, a circle is not our typical circle that we imagine, just as pi is not the same value that we are always thinking of as well.
The Euclidean geometry definition of pi is the ratio of the circumference of any circle to its diameter is 3.1416 rounded to 4 decimal places. If we adopt the Euclidean geometry definition of pi, then for any taxicab circle, the ratio of the circumference of any circle to its diameter is pi. Therefore, given the taxicab circle here, there are a total of 20 lattice points. In taxicab circle, there consists 4 times the radius r points. In our case, 4 times the radius r, 5, is 20 points. There is also a circumference of 8 times the radius r. Therefore, 8 times the radius r5 is 40 units. Then we have 8 times the radius divided by 2 times the radius is 8 times 5, the circumference, 40 units, divided by 2 times 5, the diameter 10, and the taxicab pi value is exactly 4. Therefore, in taxicab geometry, the value of pi is the constant 4 in all circles.